Okay, so here's the agenda for finite difference for multidimensional partial differential equations. First of all, I'm going to talk about domain mapping. Domain mapping actually has nothing to do with finite difference. It is more like a prerequisite of applying finite difference to most of the interesting problems we are going to encounter. This is because when we have a one spatial dimension, the domain is, well, an interval in 1D. But anything that goes higher dimensional, we can potentially have something called geometry. Right? The domain is not necessarily a square or a rectangle or anything like that. It may even be pretty complex. We're going to learn pretty soon that finite difference is not very good at dealing with very complex geometry. But it can deal with geometry that is more than a rectangle. And that is through domain mapping. Alright, so that's what we're going to talk about first. And then, once we map a domain into a rectangular domain, we are going to study 2D finite difference on the rectangular domain. And then we're going to be talking about how to solve two-dimensional partial differential equations with finite difference. What the solution method look like in matrix form, and error and stability in 2 dimensions. Okay, so first of all, domain mapping. So finite difference is very good at handling domains that are what we call logically rectangular. That is, if you can think of a map that can map a domain that, for example, looks like this, map into a rectangular domain. The mapping may not be obvious like this. For example, in aerodynamics, we can look at an airfoil. For example, this is an airfoil. And we need to solve the flow outside the airfoil. It's not obvious how to map that into a rectangle. But people have figured out not only one way, but multiple ways to do that mapping. I'm just going to give you one example. So this is what they call a C type of meshing technique. So they basically cut a line through the trailing edge and map it like this. So then, if you basically cut it and stretch it, it looks like a rectangle, right? There is also this is called a C mesh. There is also what's called an O mesh, and you can imagine it's basically a ring around the airfoil that expands into far field. So there is a lot of cases where the mapping is not obvious, but like with enough creativity, you can think of how to map it into a rectangular domain. So here, in this case, it's pretty obvious, like the correct mapping is like this. All right. So let's talk about, once we have a mapping, how to solve differential equations on this weird domain. So let's call this domain, or did I select the same color? Let's call this domain the physical domain, and this domain the computational domain. All right. So let's say I have an equation that describes the physics on the physical domain. The question I want to ask is that, can I solve the equation on the physical domain by solving a similar but maybe different equation on the computational domain? So let's say the coordinates on the physical domain is x and y, and I have a solution u of x and y that satisfy a certain differential equation. So let me just assume for right now the differential equation is the two-dimensional Poisson's equation. So second order derivative in x plus second order derivative in y equal to a certain given f. The question is, can I, if I have a mapping between x and y, and this coordinate, let's say xi and eta, all right, these are Greek letters. Mapping, what do I mean by mapping? A mapping means I have a function that gives me x as a function of xi and eta, and y as also xi and eta. And also the inverse mapping. The inverse mapping means I have a function of xi as a function of x and y, and eta as a function of x and y. They don't have to be both explicit. Maybe one of them are explicit, the other can be implicit. So if I have these two mappings that are inverse of each other, I basically can say, okay, if xi and eta is equal to this point, through the mapping I get to this point. If xi and eta is this point, through the mapping I get to this point. If xi and eta are this point, through the mapping I get to this point. And similarly, basically I'm going to map the boundary of this rectangle into the boundary of this physical domain. And through the inverse map, I can map, the inverse map means x of xi of x prime and y prime, eta of x prime and y prime is equal to x prime. And y of xi of x prime, y prime, eta of x prime, y prime is equal to y prime. So basically, if you map it from x and y to say eta and map it back, you are going to get the same point. And also, you are mapping exactly the boundary of the computational domain into the exact boundary of the physical domain. And exactly the inside of the computational domain into the inside of the physical domain. Now, if you have that map, it is quite rare that you can solve the same equation on the computational domain. Usually, you have to solve a different equation in order to define the function. So I want to have u and x and y. But can I solve this u of x and y through solving for u of xi and eta, which is defined as u of x xi eta and y of xi eta. So if I have this u of xi eta, then I can get the corresponding solution in x and y through this mapping. Or if I want to know the solution in the physical domain at a particular x and y, I can look for the corresponding point in the xi and eta space. And if I know the solution in the xi eta space, I can know the solution in the x and y space. Now the question is, how do I solve for the u as a function of xi and eta? How do I solve for the solution at the computational space? Okay, here's the trick. The trick is to derive the differential equation in the xi and eta space through elementary multivariate calculus. And that tool we're going to use is called the chain rule. All right. Hope you all still remember that. So, let's say, for example, the second order derivative of u as a function of x is actually the first order derivative of u, right? So, if we're able to deal with first order derivative, we can deal with second order derivative. And the first order derivative of u is actually equal to x is equal to partial u partial xi times partial xi partial eta, not partial eta, partial x, plus what? Partial u partial eta times partial eta partial y. And these two Oh, partial x. Thank you. These two are the partial derivative of the mapping between x and y to c and eta. Alright. And if you look at the second order derivative, then it is equal to the first order derivative applied to this, which is equal to partial eta of, instead of u, I have the first order derivative, which is expanded. Let me just write it down. Partial eta of partial u partial x times partial c partial x plus partial u, no, not partial u, partial eta of partial u partial x times partial eta partial x. Right, because I'm just instead of having u here, I'm having partial u partial x here. And then I substitute this into both this and this. Alright, I'm gonna get a lot more terms. I'm gonna get how many terms? I'm gonna get each of these are actually two terms, and if you write down the derivative of the product, each product is gonna become two terms. So you're gonna get 1, 2. If you substitute this, you're gonna get 4 terms, and 4 terms, you're gonna get 8 terms. I'm not gonna write down here, but you get 8 terms involving first order derivative and second order derivatives of eta and c. But the point is, you have removed all partial derivatives with respect to x and y, right? We have represented everything in terms of the partial derivative of the solution u with respect to c and eta. The same thing can be done with partial square u partial y square is equal to another 8 terms that involves the derivative of u with respect to c and eta. You're going to have first order derivative and second order derivatives. And hopefully, if you construct your mapping to be, if you're aware of all these derivatives, then hopefully you can construct your mapping in such a way that as many of these terms are as you can make them is 0, right? That would be ideal. And so basically, the Poisson's equation, instead of as a function of the derivatives in x and y, is going to be expanded into something times the derivative with respect to c and something with respect to the derivative of eta, something that has derivative in both c and eta, something times the derivative just in c, something times just the derivative in eta, and perhaps something just times the solution u is equal to f. And of course, if you want to construct a map so that solving the equation is easy, you should do it so that a lot of these terms are 0. Okay, now we have transformed the equation in x and y into equation in c and eta. And now we can study how to solve an equation in a regular space, which is where c and eta lives in. So this is, think of this as c and eta, right? This is what we have if we have a mapping. But we are going to use x and y in this from now on, because if you have a mapping, you can think of them just as c and eta. All right. So here we are starting to discuss how to solve the equation in this kind of regular domain. Any questions on the mapping?